Hello everybody and welcome to today's virtual Eclipse community meetup. We are lucky to have joining us Simon Hoinkis introducing Eclipse iceoryx Almond. Simon was also recently announced as one of the 5 early bird sessions for EclipseCon 2021 with his session titled Open Source in Safety Critical Systems, How Does That Work? So be sure to tune in again in October for that. If you have any questions for Simon throughout the presentation, please feel free to ask them in the chat or using the Ask a Question tab along the bottom of your screen. Without any delay, Simon, over to you.
Hi, and welcome from my side to today's virtual Eclipse community meetup. I'm going to be introducing our latest Eclipse iceoryx release called Almond today. Up front, a bit about myself. So in the last couple of years, I worked mainly as a software architect at Bosch for driver assistance systems. And today, I now work at Apex.AI, where I mainly work as a maintainer for Eclipse iceoryx and also work on our product Apex middleware, which is based on iceoryx. Let's jump right into, let's have a look at the agenda first. So first I'm going to motivate and talk about why inter-process communication, also short IPC, is important. I'm going to introduce you to Eclipse iceoryx in detail, and then briefly dive into the new features that we have created with Almond. Shortly present you the updated C++ API, also our new C API, the M2M Communication feature, and 2 really cool new building blocks, the weight set and the listener. Next up, I'm going to also talk a bit about the integration into ROS2 Galactic, and conclude with a brief outlook of our next release and our future work. All right, why is IPC important even today? Well, autonomous systems, they are becoming more and more ubiquitous. So they are in our daily lives. No matter it's your cleaning robot at home, a mining vehicle that does autonomous mining, or your Waymo car, they are in our daily lives. And what do all have these systems in common? Well, they have in common that, first of all, they have a lot of sensors. So they really have, for example, LiDAR or radio video sensors. And all of these sensors collect a huge amount of data. And the second thing they have in common is roughly this feedback loop that you can see here. So first, as I told you already, they have to sense the environment. They use a lot of sensors for that. Then they have to plan and analyze the situation and, for example, plan a route to avoid any kind of obstacles. And then in the end, they have to act. So they have to execute the plan and drive, for example, as in a specific route. And usually on these modern systems, you are nowadays using an operating system. For example, QNX is one of the operating systems that is quite popular in the safety community. And with these operating systems, you have different applications and they run in their own virtualized address space. So they cannot see each other's memory. And that's actually a good thing, because if you would think here, we would develop such a system, then, for example, we would have a sense application, a planning application, and an acting application. They would be decoupled. Yeah? They would be basically separated by concerns, and you would apply the divide and conquer principle here. And also this simplifies development, because you can develop like 3 separate applications here, and they cannot interfere with each other. But now we have the problem that they have to communicate, because the sensing application needs to send its results to the planning application, and then the plan application needs to send its results to the acting application. And this is exactly what Eclipse iceoryx is all about. So doing this inter-process communication. And this inter-process communication needs to be fast, and it needs to care also about the huge amount of data. All right, next up, I want to deep dive into Eclipse iceoryx and briefly introduce you to it. But up front, I want to look at today's system. So there's many IPC mechanisms around. Some of you might know them, for example, a socket or dbus is a quite popular IPC mechanism. There's also other middlewares around. And how these middleware or these IPC mechanisms, how do they usually work? So we have here an example. A sense app is sending data to 2 different planning apps. So for example, this could be part of an algorithm here in the planning app. And usually what happens with these systems is they copy the data towards the middleware, and then for every subscribing application, they do another copy. So you end up with a graph here, like on the right side. The latency in the runtime increases with the message size. And this is very bad, because if you have huge amount of data, your system will become slow. And exactly this is the thing that iceoryx is tackling, or the problem that iceoryx is tackling. iceoryx's unique selling point is that the latency in the runtime is independent from the message size, as you can see here on the right side. And you get now virtually limitless data transmission at constant time. And this is what we call true zero-copy inter-process communication. And iceoryx was forked off a middleware framework back at Bosch, so about 6 years ago. The predecessor of iceoryx is used on microcontrollers and runs out there on millions of devices. So it's very likely that you have the predecessor also in your car today, for driver assistance applications mainly. And I will now look at the 3 main points that define iceoryx, to say. So first of all, the first point being it's very fast. Yeah, so it's made to transfer gigabytes. If you look at a typical Linux system, yeah, like your Ubuntu machine, the message transfer latency is about 1 microsecond. But at the same time, and this is the second point, it's also flexible. Yeah, it runs today. Almond runs on QNX, Linux, and macOS. And with the 2.0 release, we also plan to support Windows. However, I have to state, only QNX will be the target that is really used, let's say, for production systems. It's also integrated in some other frameworks, for example, the ecal middleware from Continental. And we also at Apex, we built our Apex middleware based on Eclipse iceoryx. It's also integrated in the RTA VRTE from ETAS. This is a subsidiary of Bosch. And recently, it was also integrated into Eclipse Cyclone DDS, which is maintained by AD-Link, but more on that later. And new with Almond, you are really able to use now iceoryx as a standalone API. So with our very, very user-friendly new C++ API, this is also possible. And the third point here being iceoryx is also dependable. So it's developed according to automotive requirements. And what does this mean? Well, iceoryx is not your usual open source project. For example, we've recently teamed up with a company called Exivian, and we run, or we will run in future, with all the pull requests, a static code analysis that performs a code analysis according to the AutoSAR C++ 14 rule set. And this is a requirement that comes, for example, from the automotive industry. And this will also be free of charge for a low number of contributors. And additionally, we have many STL implementations that are optimized for safety. So for example, in our fixed vector implementation, if you are accessing an element of the vector, always there will be an out-of-bounds checks. So no out-of-bounds accesses are possible. All right. This zero copy mechanism that we use, it is lock-free, and it uses so-called memory chunks in memory pools that live in the shared memory. Here in this picture, they are depicted as these small wagons. I won't go into more details here, but if you want to learn more about the inner workings of iceoryx, you can go and check out our talk that we held at FOSDEM a couple of years ago. All right. So let's dive into the new features of the Almond release. I will give you a brief overview. So we will talk about, or I will talk about the updated C++ API, also the C API, which is delivered as a separate CMake target, so it's basically sitting on top of the C++ API. I will introduce you to the new M2M publish-subscribe communication feature. Also mention the event-based notification with the new building blocks, WeightSet and Listener. Also new in the release is macOS support and also a bridge to Eclipse Cyclone DDS. And now I'll talk more in detail about the first 4 points here on the list. But up front, I want to mention that throughout the next slides, there will be always 3 applications being involved in the examples. So meaning that there's a publishing application which sends data to a subscriber application. And additionally, there's Rowdy involved. Rowdy is our daemon. So it basically doesn't participate inside the communication, but it sets up the shared memory, and up front, the publisher and the subscriber, they have to register with Rowdy in order to be able to set up the communication. All right, let's dive into the updated C++ API. So always on the next slides, you will find the respective example here on the bottom of the slide for you to check out later. First, what we have to do, we're looking at the publisher side now. We have to create our publisher object. And as you can see here in the template parameter, we have to supply the data type that we're transferring. Additionally, as the first argument of the constructor, we have to also supply what we call service description. And the service description is made up of 3 different strings. So here, radar, front, left, and object. And these 3 strings, they are modeled after the orders are modeled of service communication. So the first string is basically the service. This is an abstract service, here radar. And then the second string is basically the instantiation of this abstract service. So here, the front left radar. And the last string defines what is being actually transmitted. So because here we are transmitting a radar object, in the example, we call this object. And then what is very important, all these 3 strings, they have to match with the subscriber. And only then Rowdy is connecting the publisher and the subscriber. All right, but now we want to send data to our publisher, to our subscriber. So we loan memory in the beginning from the middleware. And what is important here is that loan returns us a so-called expected. This is a Rust-inspired construct, so it can return us either the value that we're expecting or an error. And this expected has 2 methods. So one for the happy path and one for the sad path. So for the happy path, we have the and-then method, and we can supply this and-then method a callable. Here in this example, this is a lambda that we supply. And you can read this like a story. So the publisher loans memory, and if this was successful, and then is being executed. So this is the happy path. And as you can see here, we can then access our sample, write some data to our sample. And in the end, after we've finished writing data, we can send the sample, publish it, and from then on, it will be available to the subscribers. All right, and what if loan fails? Yeah, for example, you have to statically define the memory inside shared memory. And if we send too fast new data, it can be, for example, happen that we get an out of memory, so we can't loan anymore. Yeah, the middleware has run out of memory, and we have to handle the sad case as well, or the sad path as well. And we do this with the or else case. So basically, if loaning fails, our expected will call here the callable that we would provide in the or else call. And here we just inform the user that there was a problem, and the user can then react on this. All right, this was the publishing side. Let's jump to the subscribing side. It's again very symmetric here. We have to supply the data type and exactly the same service description consisting out of these 3 strings. And then we can take data. So what is important, we're always working directly inside the shared memory. So we take the data and directly access shared memory here. And take again, like with loan, returns an expected. And in the happy path, if the taking was successful, the and then method is called, or the callable this was applied in the and then method. And you have to notice here that this sample that is being passed as a parameter here is const. So the user, or in general, all the subscribers are not allowed to manipulate this data, because at the same time, another subscriber could be reading this data and then it would be corrupted, and this is not possible. This is why this data is const. And in the happy path, we can then read out our data and print it onto the screen. And if there was no new data package being sent, then we call, so we basically call the or else pass, and we have to check here first if actually there was this case that no new chunk was being sent. And if this was a real error, let's say, so not just the case that our publisher in the meantime didn't send any new data, then we inform the user again about this error, and basically the user can react on this. All right, this was the updated C++ API. And now I want to give you a short demonstration about this. I've prepared here an example. This was recorded with ASCII Cinema, and I will just press play here so you will get a feeling how working and developing with iceoryx feels like. So in the beginning, you can see it in the lower screen. I will pause it here for a second. We have started Rowdy, our daemon, and then you can see here there was no config file being found. So in this config file, you can basically, or the user can basically define the shared memory or the data structure that lives in the shared memory. So what kind of memory, etc., etc. And you can also see that there's 2 shared memory segments being created. So the first one is the iceoryx management segments. This is where all the publishers and subscribers and the metadata lives. And the second one is the one for the payload data. So this is where actually our data transmission is happening. All right, and now we're good to go. We can start a subscriber. The subscriber also maps these 2 shared memory segments. We start the publisher, does the same and starts publishing its data. And here it's sending the values 5 times, so we'll receive it also 5 times on the other end. All right, that was it already. So this was the example where we've basically exchanged data with iceoryx. And now next up is the new C API. And what is important now about the C API, the difference to the C++ API, besides the language, is now that this API is untyped. So the middleware is not aware of the data type that is being transmitted. And we also have an untyped C++ API, but it's very similar, besides, of course, the language, to the new C API. And in general, the C API is modeled also after what you've just seen. So I will walk you through. First of all, we have to create an additional storage here for our publisher. And then basically what we do is here call the constructor. In C, this is here done via an init method. And we give the publisher the storage. We also supply the very same service description, and the last parameter here is an optional publisher option struct that can be used to manipulate the behavior of the publisher. All right, and as before, we do the same. We loan the chunk, but before loaning, we have to create our void pointer. So as I mentioned earlier, we are not supplying the data type here, but the whole C API is untyped. So then we loan the chunk from the middleware, basically supplying our publisher, the user payload pointer, and then additionally the size of the object or of the data type that we want to send to the subscriber. And if loaning was successful, we first have to cast our void pointer to the actual radar object pointer. Then we can start filling in the data like we've done before. And in the very end, publish this chunk now for the subscribers to be able to see. And again, if loaning was unsuccessful, we inform the user, and the user can act accordingly here. All right, now let's jump to the subscriber side. With the subscriber side, it's again very similar. First, we have to create this additional storage, call the constructor, and in the init method, and supply as well the very same service description here. Then we have to create our user payload pointer, and notice again here it's const. Yeah, as subscribers, we're not allowed to manipulate the data. This is very important. And then we can take the chunk, and if taking was successful, we can read out the data. Of course, beforehand, we have to cast the void pointer back to the type that we supplied in the publisher. It has to be the very same type, and we can read it out. And at the very end, what has to be additionally done in order to release the data or tell the middleware for the internal reference counting, there's to be able to recycle this chunk to release it. All right, and next up, I want to briefly discuss the new M2M communication feature. So what does this mean? So before the Almond release, it was only possible to communicate in a 1-to-N manner. So one publisher and many subscribers. One of our maintainers created for Almond a lock-free multi-producer, multi-consumer queue. And with this queue, it's now possible to use more than one publisher. So you can have many publishers and many subscribers onto the very same topic. And both the communications will be lock-free and thread-safe. If you want to try it out yourself, you can have a look at the example here at the bottom. All right. Next, we're going to jump a bit to the new WeightSet and listener building blocks. So a bit of history maybe up front. So traditionally, for example, in the driver assistance business, in the automotive industry, a lot of polling was used. So what do I mean by polling? You had, for example, a multi-core system where a second core was waiting for data of the first core. Yeah, for example, remember this feedback loop, sense, plan, act that I introduced in the beginning. And then the second core would need data to be for its processing, for the algorithms. So it would constantly do a busy wait and asking, is there new data? Is there new data? And this would just burn CPU cycles, but it was sensible in order to reduce the overall latency of the system. Because if there was new data, we instantly want to also start a calculation on this new data. And as said before, this burns CPU cycles. Yeah, so this is a busy wait, and this should be avoided in general. And when you are using an operating system like Unix, there's mechanisms to avoid this. And we use these mechanisms now with the WeightSet and the listener building blocks. But let's dive into the example. So first the WeightSet, and I will be just looking at the subscriber side here. And the WeightSet has some more features, but I will only be looking at this has new data feature now. All right, so in the beginning, we have to create the WeightSet and the subscriber, and then attach the subscriber to the WeightSet. And then we will call wait on the WeightSet. And this will not be a busy wait here, but the operating system will set the thread to sleep here. And now imagine a publisher is sending data, and instantly afterwards, our wait will return, the thread will wake up, and wait will return, and wait will return a so-called notification vector. And this notification vector basically contains the reason for the wake up. Yeah, and we can, with this notification vector, find out the respective subscriber that has received new data. For example, you could imagine there could be more than one subscriber being attached. So we loop over this notification vector, get the data then from the respective subscriber, run our algorithm, and jump back to wait. And then we're ready to go and wait for new data. And this was not a busy wait. All right, next here on the right side, I want to cover the same thing for the listener. The listener is a bit more simple. So the user basically has to only do two things. This is here on the left side. He has to create the listener and the subscriber, attach the subscriber to the listener, and at the very same time provide a callback. And that's all. It is everything the user has to do. And what's happening inside is depicted on the right side here. So the user has not to care about this. Basically, in the thread inside the listener, we do the very same thing. We wait with our mechanism on the new data, on the signal from the publisher. And if the publisher has sent us new data, we will wake up and call the user-defined callback. Then we can get the data from the subscriber, run our algorithm, and basically return, and the thread will go to sleep again and wait for the next round of data. And again, also this mechanism is not a busy wait. And with these mechanisms, both the listener and the wait set, you are able to avoid polling and not burn any very precious CPU time. All right. In the next section, I want to talk a bit about the integration of Eclipse iceoryx into ROS2 Galactic. ROS2 stands for Robot Operating System and is the most popular open source framework for today's autonomous systems. And at Apex, we build our main product, Apex.AI, also based on ROS. And on the right side here, you can see the architecture of ROS. I will walk you through now. You can see the user applications on the very top. They are called ROS nodes in the ROS terminology, and they are written by the user. Yeah? So this is the only part that, for example, where your algorithms would run. And then on the lower bottom, we can find the ROS client library, C++, RCLCPP. There's also a Python binding, but we focus today on the RCLCPP. Then underneath, there's the so-called ROS client library. This is basically the heart. This is where all the magic of ROS happens. And underneath, you have a so-called RMW interface. This stands for the ROS middleware interface and is meant to be used with third-party DDS implementations. And such a DDS implementation is Eclipse Cyclone DDS. And since the ROS2 Galactic release, which I presume was released about like a month ago or 2 weeks, Eclipse Cyclone DDS is the default middleware. And what you can now do is, with the official Galactic releases, you can enable iceoryx, because it was integrated into Cyclone DDS, by a runtime switch. And the reason for that being that you can use then the blazing fast zero copy mechanisms of iceoryx. And for you to give you a feeling, at the data size of 1 megabyte, you roughly get 3 times faster compared with a plain vanilla Eclipse Cyclone DDS. And also in the future, we plan to improve this. So yeah, stay tuned for that, definitely. All right, an in-depth hands-on session with some demo will happen on the 21st of July, and this will be done by Matthias Kielert, also one of the Eclipse iceoryx maintainers. So also watch the Twitter channel of Eclipse or or maybe also the LinkedIn channel, whatever you prefer. All right. Now I want to conclude the talk with a brief outlook of the next features that we've planned for the 2.0 release. The 2.0 release will most likely be released, let's say, end of the year, Q4. It will contain two main features. So first, the request response communication that we're currently working on, and a major refactoring of the service discovery. This Almond release, the 1.0 release, is a long-term stable version, and it will be supported exactly for 1 year, at least this is our current plan, until 22 mid-April. And also we will work on for the iceoryx hoofs library to become more independent. And I want to talk on the next slide a bit more in detail about this and introduce you also to iceoryx hoofs. So what is iceoryx hoofs actually? Well, it is a utility library, and it stands for Handy Objects Optimized for Safety. And it's basically the building blocks of iceoryx. Yeah, this is also why it's called hoofs. Same as iceoryx or the other part of iceoryx, it's written in modern C++ 14, and it contains some backports from C++ 17 and C++ 20. So for example, the optional or the variant, these would be examples. In general, we try to be compatible with the STL where possible. But yeah, if you have safety in mind, it's not always possible. And also additionally, the dependencies to the STL in general shall be kept to a minimum. But yeah, I mean, we have dependencies now, but yeah, only where it's really necessary. This is the goal here. So in summary, you can say hoofs is a lightweight STL implementation that keeps safety in mind. And now on the right side, let's have a look actually what is inside. So we have many different namespaces here. For example, the CXX namespace. This contains some well-known constructs from the STL that were optimized for safety. So for example, a fixed string, like the optional and the variant that I mentioned before, or also a fixed vector. Then a second namespace that could be quite interesting for you is the concurrent namespace. This contains concurrent constructs, for example, a safely overflowing FIFO. It also contains a smart lock wrapper that can make any data structure thread safe, and the lock-free multi-producer, multi-consumer queue that I've mentioned before. Also, we have the POSIX namespace in hoofs, and this contains many POSIX abstractions, so for example, a semaphore, mutexes, or shed memory. Additionally, there's also a logging namespace that contains some logging infrastructure. There's also a units namespace that this aims to be a super lightweight alternative to STD Chrono that we're going to use for iceoryx. And last but not least, there's also the design pattern namespace, which contains like generic design patterns that we use throughout iceoryx. And what is now very neat is, although this is developed in the iceoryx repository, it is supplied and delivered or can be used as a separate CMake target. So you can use it completely independent of the rest of the code base of iceoryx. And our vision now is that we want to create somehow the boost library for the safety world. And if any of you guys is interested into this, be sure to ping us. And yeah, we would love you to jump on board of our initiative of strengthening such a library, because in the end, in our experience, the safety world is always a bit different. Yeah, you have to always take more care when developing these kind of building blocks. All right, and with that being said, I want to wrap up today's talk and invite you to fork iceoryx on GitHub. And if you would like to, you can also check out our website and get the full API specification. And now I will end the talk and answer possible questions. Are there any questions?
Awesome. Well, thank you, Simon, for that presentation. And at this point, we don't have any questions. So what I'll do is just go through some news items that I want to touch on and give some people some time to get their questions in still. So if you have a question for Simon, please feel free to use the chat or the Ask a Question tab. And we will ask those just after these news items. So the next virtual Eclipse community meetup, as Simon mentioned, will be on July 20th, when Simon's colleague Matthias Killat joins us to present using zero-copy data transfer in ROS2. This is another session focused on Eclipse iceoryx. So be sure to follow us on Crowdcast, as we will be announcing the opening a registration for that session in the coming days. As I mentioned earlier, Simon was also named one of our early bird speakers for EclipseCon. The call for proposals for EclipseCon is still open until June 15th. So if you are interested in speaking at EclipseCon 2021, I would encourage you to submit a proposal anytime before June 15th, and you can do that by using the link I'm about to post in the chat, and it's in there now. And finally, we hope to bring our audience more virtual Eclipse community meetups in the coming months. This is our most established and oldest webinar stream in our virtual events program, and it's open to any Eclipse technology. So if you're working on a project and you want to raise awareness for your work, get feedback, or just share an interesting story, feel free to sign up to present a virtual Eclipse community meetup using the link in the chat that I am about to post here. And I see that we did get a question from the audience. From Brett. So he asks, are there any facilities to modify the behavior of Roundy at runtime?
Okay, cool. Yeah, thanks for the question, Brett. It's actually a very good question. So I think you mean to modify probably the memory setup of Rowdy. So if we go back in the slides a bit, jump here to this example. Actually, the memory is completely static. So if you have the setup here, you start Rowdy, you read in the memory configuration that can be supplied by the user. So currently we use the TOML format for this. And from then on, it's completely static. So the memory, for safety reasons, cannot be adapted anymore. Yeah, this is for the reason that if you would, for example, use the heap, like in traditional computer systems, you would get the problem that you will have memory fragmentation, which then at some point could lead to out-of-memory problems, which you want to avoid to the utmost in safety systems. And so this is why all the memory is static, but what is dynamic is actually the startup of the applications. So if I start Rowdy, like you've seen in the example earlier, then I start my publisher application. Rowdy will not know about the subscriber application. So only when I start my subscriber application internally in the shared memory data structure, they are being connected. So this is currently done dynamically. I hope this answers your question.
Yeah, I think that was a good answer. And again, we do have a few minutes left here, so please feel free to ask your question in the chat or the Ask a Question tab. But yeah, thank you everybody for registering today and joining us, and thank you, Simon, for that amazing presentation. All right, everyone, if there are no more questions, we will wrap up. Enjoy the rest of your day, and Simon, thank you again.
Yeah, thanks, and see you. Bye.